All right, hello everyone, and welcome to our November AstroCheminar, the monthly seminar series hosted by the American Chemical Society Astrochemistry Subdivision. My name is Kyle Crabtree. I'm chair of the subdivision right now, and I'm happy that you're here joining us today. We have two really great talks lined up for you. Before we get to them, just a couple of brief announcements. I want to encourage you, if you haven't already, to please check out our division website and our YouTube channel for more information about what's going on in astrochemistry and recordings of our past AstroCheminar events. It looks like Chris is posting links to those places, to those sites in the chat right now. The other announcement that I want to let you know about is the Astrochemistry Discussions group has announced that their next event is 1 week from today, next Wednesday, and they're going to be talks on comets. So Comet Day is next Wednesday at AstroChem Discussions. For more on that, you can check their website. I think it's at astrochemdiscussions.net. So with that, I'm really pleased to introduce our first speaker for today. It's Joan Enrique-Romero. So Dr. Enrique-Romero received his PhD in 2021 at the University of Grenoble-Alpes and the Autonomous University of Barcelona, working with Cecilia Ceccarelli and Albert Remola. And Dr. Enrique-Romero was the recipient of the 2022 ACS Astrochemistry Outstanding Dissertation Award for his thesis titled Surface Chemistry of Molecules of Astrophysical Interest, Theory and Simulations. He's currently a postdoctoral researcher at Barcelona, working in the quantum grain program under the supervision of Dr. Albert Remola. And his research involves surface astrochemistry, studying reactivity and kinetics using quantum chemistry as a toolkit. And very soon he'll be moving to Leiden University to work with Tanya Lambert. So that's what's ahead for him. So his talk today is titled A Computational Chemistry Approach for Interstellar Complex Organic Molecule Formation in the Solid Phase, Radical on Water Ice, and Radical Ice Reactivity. So with that, happy to hand things over. Joan, please take it away.
Thank you very much for the nice introduction. Hello, everyone. Good evening from Barcelona. Today, I will speak to you about first work that is part of my PhD thesis. This radical chemistry on water ices, and then secondly, our latest work on icon formation, in which we investigate radical ice chemistry. So this is all about the formation of interstellar complex organic molecules, or icons for short. And you can define them as those molecules found in the interstellar medium containing at least 6 atoms. One of them at least being carbon, so that they are all organic. And some examples could be glycol, aldehyde, and formamide. So they look like the organics that you could find on Earth. And these molecules are important for astrochemists because they represent the dawn of organic chemistry. They are found in a wide variety of environments. And I have here an example from one of my colleagues in which we have 2 outflows driven by 2 protostars sitting here in the middle. This is the Iris 4A system. And each different color here is a different interstellar complex organic molecule emitting in those regions. And this is just one example because we can see them all all over the different phases of star formation. Additionally, icons could hold a large amount of the available interstellar carbon, and they are possibly inherited, at least in part, by solar system bodies, so that they are considered as the bricks for more complex prebiotic molecules, and so they could be connected somehow to the origin of life in the universe. Nevertheless, explaining how these molecules are formed and how do they evolve is an actual challenge for astrochemists. And nowadays, we have 2 classical paradigms trying to explain them. Their presence in the universe. And it all starts in the initial stages of star formation in the prestellar core, in which we have the growth of these interstellar ices on top of interstellar dust grains, thanks to halogenation and oxidation reactions that happen in situ on top of these surfaces after the accretion of simple species from the gas phase. And this leads to water-dominated ices that also contain different molecules in smaller quantities like CO2, methanol, formaldehyde, methane, etc. And depending on how these ices evolve, we have the 2 different paradigms. In the first one, we have that these iced species are released to the gas phase, and then in the gas phase, they undergo different reactions that lead to the formation of these complex organic molecules. And on the other hand, we have the only grain mechanism in which there is some mantle processing, some ice mantle processing leading to the formation of radicals. And then these radicals, at some point during the evolution of the protostar, thermally diffuse on the surface of these ices. They meet, they react in a wireless way, and then they form these icons. And later on, they are released in the gas phase. My work for the first part of the talk has been focused mainly on this part, specifically on the point at which the two radicals are about to react. But nowadays, we have many other possibilities, and we have a wider view of astrochemistry, in which we know that there can be this partial hydrogenation at the early stages, leading to radicals, as well as non-thermal mechanisms for the release of this species into the gas phase. And non-diffusive mechanisms have also been put forward, and I will come back to this later on. Now, coming back to my subject, the questions I was making myself during the PhD were basically these three. So are these radical-radical reactions actually wireless? And are there any competing reactions? And for this second question, what I did is to investigate two kinds of reactions: the radical coupling leading to the formation of icons, and the hydrogen abstraction reactions, which you will see later on, which are basically the opposite. And also whether if there are some surface effects or not. And in this case, I will not speak much about this in this talk, but you can go see the papers, or you can ask me later. So to do this, I employ computational quantum chemistry. And what I do is to basically look for energy barriers on the processes that I am interested on. And in this case, I have employed density functional theory, which is a cost-effective methodology for, as you will see, the size of the systems that I have been working with. And in addition to that, I have employed different approximations that are needed to treat properly at a theoretical level the complexity, the electronic complexity of singlet biradical systems, as two radicals sitting one next to the other could be. Regarding the ice surface, we took two extreme cases, two extreme, let's say, approaches. The first one is this small cluster made of 18 water molecules, in which I call it open surface-like because I have run the chemistry simulations on top of it. So there is nothing in the middle, let's say, there is nothing around it. The two radicals would sit one here and another over there, maybe. And so they could resemble a flat surface-like system. Meanwhile, the second model has a larger size, and it's big enough to host this small cavity here. And so I have studied the radical chemistry in this cavity to see whether if there are some effects coming from the larger amount of intermolecular interactions. And the initial point for this kind of systems looks like this, in which I have two radicals, in this case, the methyl radical and the methoxy radical over there, sitting in neighboring binding sites. And I do this manually by trying to maximize the number of intermolecular interactions so that they are well attached to the surface. And then I start to run the geometry optimizations and all the processes needed to unveil the chemistry of the systems. And during the PhD, what I did is to tackle this whole list of systems here. It's 11 systems and 22 reactions, and they are different combinations of formyl and methyl, amidogen, methoxy, and hydroxymethyl radicals. So that I have been focusing on the formation of these different icons here, going from acetaldehyde formamide all the way down to dimethyl peroxide, as well as all the possible exothermic channels in which there has been one H atom from one of the radicals given to the other. And I repeat, I only take into account those channels that are exothermic. So in many cases, I only have one possibility. And in others, like here, I can have two possibilities. So this H atom going there, or one of these H atoms going over there. For the first case, the formation of acetaldehydes, we have looked into it with more details. And with the energy barriers, we calculated reaction rate constants, and with the binding energies, we calculated diffusion and disruption rate constants. And with this information, we calculated reaction efficiencies, which are nothing but the probability for one of the two reactions to take place once the two radicals have met. Here, for the diffusion barriers, we assumed that these barriers are a fraction of those of desorption, as it is normally done in astrochemical models. And these fractions, we took them to be 30, 40, and 50% of the disruption energy barrier. And the choice of this diffusion energy barrier has huge consequences on the outcome of the efficiency of the reaction, so that when you go and see what happens for the formation of acetaldehyde or CO and CH4, depending on this diffusion to desorption energy ratio, you have that those cases where you take diffusion to desorption to be larger than 0.4, they are like around unity. So both channels are equally efficient, so they are equally probable. Meanwhile, when you go down to 0.3, then you observe that there is a temperature-dependent profile for both reactions. And here in the solid line, there is the formation of acetaldehyde, and in this dashed one, there is the formation of CH4 and CO. And as you can see, acetaldehyde is never efficiently produced in our model. Meanwhile, CO and CH4 is only efficiently produced at very low temperatures thanks to quantum tunneling. So depending on what you choose for this diffusion to desorption, you can have a completely different chemistry happening. Nowadays, in the literature, the values that more often appear lie between 0.3 and 0.4. And this comes from different experiments and simulations. And so when we did the estimations of these efficiencies for the rest of systems, we took a value in the middle. So we assume that the diffusion to desorption energy value, energy barrier, would be something in between that. So it would be 0.35. And the results for this estimation of these efficiencies are shown in this table here, in which you have the results for the open surface like and the cavity, and for each one of the possible outcomes of the reaction for each one of the systems that I studied. And each color indicates a different value of efficiency. So green colors indicate an efficiency of unity, red colors indicate an efficiency of 0, orange is roughly unity, and then the two color ones indicate those cases in which quantum tunneling could play a very important role at low temperatures. So that low temperatures, the efficiency could become unity. And this is a qualitative statement, because what we did is to calculate the crossover temperature. And if this temperature could be large enough, then we just assume this the system to be categorized into this classification. So the results from this table can be are summarized here. And so we have 4 cases that may actually happen without any kind of competition. And these are those cases that basically don't have a competing channel, or those cases where the competition is not possible. For example, the formation of ethanol. Then we have several cases where there is this competition between the coupling and the H abstraction, and most of them contain as a reactant an HCO radical, and it seems like this radical can easily give away one of its H atoms. And finally, we have a clearly unlikely case. This is dimethyl peroxide, in which the methoxy radicals are so stable that the barriers are very high, and they are stabilized. These radicals are stabilized because the radical electron sits on top of the oxygen, and the oxygen is establishing interaction with the water molecule, so it is less prone to react. Finally, in the case of acetaldehyde, we do not observe its formation in our cavity model, but we do see it in the open surface like. So it will depend completely on the geometry, on the locality of the ice surface. Nevertheless, this radical mechanism has some drawbacks. First of all, is that they were considered to be barrierless, but they are actually not. There is this dependence on the emitting probability, which basically depends on radicals thermally diffusing. And additionally, there is this delicate trade-off between the diffusion and the desorption of these radicals in our astrochemical models. So it has some problems here. And so different ideas also coming from different areas have been put forward. Here I put a list of different articles that I encourage you to check on if you are interested on this topic. And I want to focus on one of our works in 2018 in which we observed that a CN radical landing on a water ice could lead to the formation of formamide. Recently, we found another candidate for such radical ice chemistry, and this is CCH, which is the simplest carbon chain molecule, which is interestingly very abundant also, or relatively abundant, in cold molecular clouds and stellar cores, right? The place where there are also ices. And the chemistry goes out as follows. We could have this CCH radical coming from the gas phase reacting with a water molecule from the surface. And then after a halogenation step, it would yield the formation of vinyl alcohol. And after 2 H additions, it could form ethanol. So the first step looks like this. Its potential energy surface looks like this. The first step is the formation of a hemibond. So these are 2 electrons coming from the oxygen and 1 electron coming from the radical that are forming this 2-center 3-electron bond. It's called a hemibond, which form this adduct here, which then can undergo a proton transfer, water-assisted proton transfer, all the way here, forming this precursor for vinyl alcohol, which is a radical, and it could take an H atom from the environment easily, leading to the formation of a closed shell molecule. And here, what you see is the different numbers here are the energetics of the process, and those numbers in parentheses are the non-0 point energy corrected values. Meanwhile, the very ones are fully corrected values. And in the end, if you look at them, you can see that the whole process is efficiently barrelless. So the first step is, you could think it is very efficient, it is, but we also saw that there is a dependence on the way CCH attaches to the surface, so that CCH could perfectly form an H bond instead of a hemibond, leading to the formation of acetylene and OH in a barrelless manner as well. So that if this happens, then for the next step, it requires a lot of energy. And given that water is such a good energy sink or a third body, I said we don't think that the final step would happen unless there is some kind of energy input. Finally, for the final step, we have the halogenation of vinyl alcohol, which the first step of this halogenation requires an energy barrier, and this energy barrier is it's about 7.4 kilojoule per mole, which is about half the energy barrier for the halogenation of Cl. And in addition, it has also a high crossover temperature, so that tunneling can dominate, rendering the whole process efficient if CCH lands with the proper orientation on the ice. So with this, I finish my talk. I leave here my summary for the 2 parts. I thank you for your attention, my collaborators, the supercomputing agencies, and I will take any questions you have.
All right, thank you, Joan, for that very nice talk. So as was posted in the chat, if you have questions for Joan, please do open up that question and answer tab at the bottom of your screen and submit them there. Alternatively, you are welcome to post questions in the chat. So to get things started off, I would like to ask, you were discussing the nature of the barrier. So there were some reactions that you said were thought to be barrierless, but you found actually had a barrier, and the CCH pathway was in fact barrierless after the 0 point correction. Have you explored those barrier heights as a function of perhaps the density functional that you use? Because I've seen in some cases like barrier heights on inference channels for radical-based reactions being really sensitive to the choice of functional.
Yeah, indeed. So what we did is to take on a density functional that works, how to say, that destroys the list, let's say. So that's, I used a Becker-Half. Sorry. I used the Becker-Half functional, and this is a great functional for a broken symmetry or biradical system calculations, because it has a set of qualities that make it to have less errors, less self-interaction errors, and to be more consistent with this kind of systems. But of course, you cannot have a functional that is good for everything. So this is probably one of the best ones for this kind of calculations. We did some, we actually did benchmark comparing with multi-reference methods, and that showed very good agreement for example, for the acetaldehyde case. But of course, you cannot say the same for any system on the universe. So you cannot put your hand in the fire that Becker-Half will work good for any system at all. So if somebody else wants to do this kind of calculations, they should definitely try first to do some sort of benchmarking as we did, or at least to check that this is not too bad for this kind of systems. And for the CCH, we also did a very thorough benchmark. And in this case, we employed two different DFT methods, omega B97 and one of the Minnesota derivatives.
Great. I guess a not really related question, but so you were talking about the water ice surface that you were modeling, and you used a geometry that had a nice cavity, and that cavity was involved in some of the reaction mechanisms. If you have an impure ice, at what, like, how much other stuff would need to be in the ice to have an effect on the structure of that cavity at the surface?
So the first thing is that the barriers that we have found for radical chemistry, they do come from the interaction of the radicals with the surface, mostly. And I say mostly because we don't have let's say a percentage of how much of the barrier comes from the barrier from the surface or not. It's basically we understand that the barrier comes basically from that interaction. So if you could have, for example, a CO pure surface, then you could have mostly no barrier at all, because that could be like a gas-phase reaction plus some interaction with the CO, because you cannot make any more H bonding. Then if you have a dirty ice, then probably radicals could be sitting on the places with a stronger interaction, and then it could entirely depend on the local structure of your ice. So if you have, for example, water and CO, likely they will not sit on top of the CO, they will sit on top of water. So you could have something similar to this, and it will depend on how is the dirtiness of this ice, let's say.
All right, thanks for those very thorough answers to those questions. I think with that, we are going to need to move on to our next talk, but thank you again, Joan. That was a very nice discussion of quantum chemistry applied for studying surface astrochemistry. And congratulations again on receiving the dissertation award.
Thank you very much.
All right, well, moving on, our next speaker today is Dr. Ugo Jacovella. Ugo received his PhD in 2017 from ETH Zurich, where he worked with Frederick Merkt on high-resolution spectroscopy of small hydrocarbon cations. Following a postdoctoral stint at ETH Zurich, and then then a second one at the University of Melbourne, working with Dr. Evan Biskey. He moved to CNRS, where he is a CNRS researcher affiliated with the University of Paris and ISMO. And the work that he's going to tell us about today is on the vacuum ultraviolet photoprocessing of interstellar PAHs. So with that, I will hand things over to you, Ugo, to take it away.
All right, cool. Thank you very much, Kai, for the nice introduction. So we're gonna shift now toward gas phase astrochemistry, and yeah, today first, thank you for the invitation. I will present one part of my research activity on this VUV photoprocessing of interstellar PAH. And so just to start with a little bit of context. So once you have those molecules in space, as most of you know, VUV radiation is ubiquitous up there. And once they get photoexcited, you have different competing processes that can occur, unimolecular processes such as, and today I will focus only on those leading to fragments, cationic fragments. So you can have isomerization, ionization, of course, or dissociative ionization. And depending on the amount of internal energy that you're depositing into the system, you can even imagine having some subsequent reactions. And of course, depending on this amount of energy, also you can vary the branching ratio between those different processes, and the fragments you are generating can exhibit different chemical activity and therefore can steer the chemical evolution in different manner depending on the region of space you are, and because of the difference of UV radiation field you can have. And so there's this recent interesting paper by Chris Hansen and co-workers on the open question of the cycle of carbon-based molecule in space. And of course, depending on where you're looking in space or what are the signature you're looking at, you can get different kind of information. And I would just want to take one example because it's really timely with the JWST, where now we'll be able to map out all this aromatic infrared band emissions, so which are emission feature most likely belonging to aromatic compounds. So you basically photoexcite them with UV or VV photon, they will relax and they will emit infrared light. And with JWST, we'll be able to map them out with unprecedented resolution, but also we'll be able to map them at different positions. So we can see the evolution depending where we are in different region, or close we are, or far we are from stars and things like this. And one of the things is people have been struggling trying to find exactly what are the molecules responsible for those emission bands. And as you can see, they're not super well resolved. So we're usually typically talking about family, trying to explain bands based on family and things. But all the models, most of the model, let's say, they will take into account the dissociation, the degrees of ionization and things like this. But often what is missing, it's mainly because we're also missing the information, and what are not in the model is all the things happen after isomerization, because of course, for those PAH, often the isomerization barrier lie in the same region as the dissociation barrier, and then you can have easily some isomerization processes occurring. And the way we're trying to produce this, usually we do laboratory astrophysical experiment where we record infrared absorption spectra of those molecules, and then we do quantum computational calculation trying to figure out what is the anharmonicity so that we can retrieve the emission spectrum of those species. But that basically limits us of having a starting point or starting path that are stable, that we can just like use a powder, heat it up or whatever. But all those strange and exotic configuration you could get after VUV excitation will be missing. And so one way of starting those VUV induced isomerization process is to use this experimental setup called Ceres. It's basically a tandem mass spectrometer. So it's an apparatus that belongs to a group at ICP constituted of Claire Romanza, Roland Thyssen, and Christian Alcaraz. The work I'll be presenting has been done also with a really good undergrad student, Corentin Rossi, and this is an associated experiment with the synchrotron Soleil and the Désir beamline, so the VUV beamline. So you can basically apply. You have a call every 6 months and we can apply. So how does it work? So you basically have your neutral precursor that you link into the ion source region that is intersected by the VUV photon. So you generate your ions, then you can mass select your ion using quadruple Maus filter. Then it's guided toward a reaction cell where you can link in your neutral reactant partner. And then the product of reaction, they are guided and confined radially with a second octuple, and then they get mass analyzed into a second quadruple and then detected. And maybe here, one important timescale is the time between the burst of the ion and the reaction cell, which is in the order of 80 microseconds. This is important because that means any isomerization that will be slower than 80 microseconds will be blind to it. And so what you can do with this machine, you can basically control the internal energy of the ions, because you can basically varying the photon energy, and so varying the amount of excess of internal energy you're depositing into the system, and you can vary the collisional energy by varying the bias on the octopole, so basically the kinetic energy with which you are bringing the ion into the reaction cell. And with that, you can measure absolute reaction cross-section, and sometimes you can even retrieve some mechanistic information. And so the technique we use is called chemical monitoring technique. So it basically means that you will look at changes in reactivity depending on the isomers you are forming. So if I take the simple example of where they have this nice triatomic molecules, where you have H-nu1, which correspond to the ionization energy to form the cationic counterpart, and H-nu2, where basically you will overcome the isomerization barrier from isomer 1 to isomer 2 and form this linear isomer. So you take the first cases where you have the reaction with this diatomic green triangle that only reacts with isomer 1. So basically below the ionization energy of isomer 1, you have no reactivity. So if this is the reaction cross-section, and as you start forming isomer 1 cations, then you will start to see an increase in the reaction cross-section. And once you pass the threshold to form isomer 2, you will redistribute your population because you normalize by the total amount of ions corresponding to the mass of the isomer 1 and isomer 2, you will start having a decrease in the reaction cross-section. And those reactions are typically either charge transfer reaction or what I call chemical reaction, where you actually form a complex, an adduct, and then you can have most likely some elimination to stabilize the system. And as I said, here you have no reaction with isomer 2, but you can take the opposite case where you have the reaction with this yellow square thingy, where you have only reactions with isomer 2. So as you go on in energy, you pass the ionization energy of either 1, no reaction, and then once you pass the energy corresponding to the appearance energy of isomer 2, you start having a signal. And so you can basically, by monitoring the change, know that you have passed the isomerization barrier. And this is actually the case we prefer because it's a background-free signal. Whereas here, when you look at the depletion, of course, then the signal-to-noise ratio is not as good, and you can also have competing process that could lead to a decrease of the reaction cross-section. And so now I will illustrate this with the interconversion pathway on the C10H8 plus surface, so mainly focusing on the interconversion between the naphthalene cation and the acetylene cation. So here is zoom on the part of the potential energy surface we care. So the global minimum here is the naphthalene cations, lying 0.8 eV above it. You have the acetylene cations, and the barrier, the interconversion barriers, depending on which routes you're looking at, will range from 3.7 up to 5.6 eV. This is based on the work by Alexander Medel and co-workers, and so the group of Paul Meyer also did some RACM modeling in there. And so what you can see is in the range of this isomerization barrier, you also have channel leading to the loss of acetylene and forming the C8H6 plus ionic fragments. But just I want to mention that even below that, you have another isomers, which will play a role at some point, which is this phenylvaline acetylene structure here. And so here we're going to look at the charge transfer reaction. So between here naphthalene cation and the durine or tetramethylbenzene. So basically the charge transfer reaction, to have a charge transfer reaction, you need to have the IP of the ionic species to be greater than the one of the neutral one. And it depends, the cross-section will depend on Franck-Condon consideration, and can also have some resonance effect. But as a rule of thumb, typically you will say that the reaction, the larger, the smaller the delta IP will be, the larger the charge transfer cross-section will be. And in the case of acetylene, you can see that the IP is lower than the one of durine, so that you will not see any charge transfer. So here what you see is result from this tandem mass spectrometer that I presented you earlier. So the top panel here is just the photoion yield. So you have the ion count. So here it's starting from naphthalene neutral precursor. And as you vary the photon energy, you can see here you have the ionization threshold of it. And what you can see is by monitoring the cross section here are two different channels. So this one corresponds to the charge transfer, and this one is the dissociative charge transfer. So you get charge transfer and then followed by the loss of CH3. And you can see as soon as you start forming naphthalene, you have a strong charge transfer reaction, and then you just slowly decrease as you increase the photon energy. And what is interesting is when you do the sampling starting from azulene, and what you can see is you have past the ionization energy of azulene, you have no reactivity, and only when you reach like this 4 eV roughly of internal energy, you start that you have an increase of this charge transfer reaction, which is basically indicating that you have the isomerization reaction from azulene cation to naphthalene cation. And I just wanted to mention that we also did the same thing looking at reaction with propine, alene, and methanol. It's a bit messier, but what was interesting is naphthalene and azulene cation are pretty unreactive, but once you passed a certain amount of internal energy, which correspond roughly to, based on work of Pohlmeier and Arachem modeling, you will form this PVA plus, which seems to have a really richer chemistry than those azulene and naphthalene cation species. And so with that, I'll just finish on this C10H8 plus part of my talk, where we show that we can basically live track and monitor isomerization of pH using ion molecule reactions. And that, so you can see here is an example starting from naphthalene and azulene, so really poor reactivity, and only this group of isomers that we tentatively assign to the PVA plus seems to have a chemistry. So it's sometimes, especially in media like in the interstellar medium, where you have a lot of energetic processes, that the importance of isomers that are not necessarily the most stable one can play an important role in the steering the chemistry up there. And one question I always ask myself is, I mean, you have a few charge transfer reaction in the astrochemical model for small system, but most of the time they are not taken into account for large system. But when you look at it, I mean, here you can see typically the reactivity, ion molecule reactivity is a few square angstrom, but for charge transfer it can be really crazy, up to 300. So I'm just wondering how those kind of reaction can play a role in modeling the chemistry in interstellar regions. And now I'll move to the VOV photodissociation of protonated cyanoaromatics. I mean, as you probably know, there are a lot of aromatics nitrile species that has been detecting in TMC1, and even in some, for the case of benzonitrile in pre-stellar and protostellar sources. And there is clearly a lack of the understanding of what happened there, because always it seems that the abundance derived from the observed transition is always larger than what the chemical model are predicting. And so here to investigate those, we use another experimental setup, which is also in Soleil, also on the Desir beamline. And so it's an ion trap called SRMS2. This has been done with some people from Soleil, also Alexandre Giuliani and Laurent Naon, some mates back from Australia, Chris Hansen and Adam Trevitt, and Jennifer Noble from the University of Aix-Marseille. So here what happens is you can generate ion using either an electrospray source, or you can also use an atmospheric chemical ionization source, or an atmospheric photoionization source. Then you guide your ion into a trap. You can do a first MS stage, so you will select only the ion of interest, and then you get the light from the synchrotron that you monochromatize, and you can irradiate it into your trap and just monitor then the mass of the photofragment produced. And the first example will be, of course, on the protonated benzonitrile. And why the protonated one? I mean, it's simply because there's been a bunch of neutral cyano aromatics detected, and in those medium you have a lot of H3 plus. So, and most of the positively charged species detected in space have been detecting under the protonated form. So that would be most logical start. And so here what you can see is so the total photo product yield. It's basically summing up all the channel of all the lost channel. And so this has been recorded using a cryogenically cool ion trap in Marseille. And here's a result from Soleil. So you can see a good overlap, and this allowed us to really record the spectra starting from the S0, S1 transition. And here are the channels. So you can see the main channel is the loss of HCN or HNC. And interestingly, so you will form the phenilium. So that will be in blue, but this phenilium is highly reactive with water, residual water present in the trap, and form this protonated phenyl species. And you have also a minor channel corresponding to the loss of cyanoacetylene. And so, as I said, also we have those reactions. So basically the pressure in the trap is around 10 to the minus 3 millibar, which would correspond to 10 to 20 collision per microsecond. This is probably why this protonated phenyl species can survive and don't need to lose this nitrogen. But what is interesting is you can clearly see a change of reactivity around here. And if you plot the dissociative branching ratio, you can see that it actually some kind of a resonance effect, this change of reactivity. And here I just plotted few of the molecular orbital corresponding to some of the excited states. And what you can see is here it's S2, S8, and S12. And actually S12 is the only one which is not a typical pi-pi star transition. You can see that you really have a disruption of this pi system. And one hypothesis we had is maybe once you excite these S12 states, you start having some ring opening mechanisms, which of course will prevent and hamper this formation of protonated phenyl. And what is interesting is this phenylium reactivity. I mean, the phenyl is a key species in the formation route of aromatics. I mean, starting from the most basic one, the benzene. So where you will get the radiative association of phenylium with H2, followed by dissociative recombination to form the neutral benzene. And there are a bunch of, I mean, here it's just one example, but a bunch of ion molecule work where you can form adduct, and then you can have various ways of eliminating the excess of energy and forming a zoo of PA, basically. But so it might be possible that this protonated benzonitrile could play a role in the PA growth, but it will be in an indirect manner because you first need to photofragment and then the photofragments need to react. So it will be at least a two-step process, which means it should be a slow mechanism if it plays a role at all. And so then we start looking at larger cyano-PA. But here's the same story. It's basically you see mainly the loss of HCN or HNC, and it still reacts strongly. So this aryl cation, this mono dehydrogenated PA cations react strongly with water, and we start also seeing the beginning of the dications. But I mean, we're quite surprised because even with 2 or 3 cycles, we still see some structures. And then we did the same game of plotting the relaxation branching ratio. And what is funny here is you can see in this case we don't have this resonance phenomenon in the reactivity, but we do have a crossover point. For instance, here in the case of the 1 and 2 cyanonaphthalene. And what is interesting is if we move to the 3 cycles, so here the crossover appears at much lower internal energy, whereas here it doesn't even happen at all. So you always get the higher yield for the unreactive species. And this can be tentatively rationalized, and this is work in progress, because when you look at those aryl cations, phenylium, naphthylium, and so on, So basically, when you start with phenylium, the singlet state is the most stable one. And then as you increase the size, the singlet to triplet gaps will shrink, and basically they will be almost isoenergetic for the naphthelium. Whereas here at 3 cycle already, it should be the triplet state, the most stable one. But what you have to keep in mind, of course, when we generate those aryl cations through photodissociation to photolysis of the cyano PAR, we probably form those aryl cation with a certain spread or a certain distribution of internal energy. So we probably form the two of them. But the fact that here it's just like the crossover happens at earlier and here it doesn't happen at all, probably like really reflect this change in the singlet triplet gap. And so, and the fact that again here we can form some photo fragments that are highly reactive, maybe indicate the importance of top-down mechanism even for small species. I mean, those is what I call small species. And also the importance, maybe the potential importance of triplet state chemistry in space. And just as a quick perspective, a teaser on future work, because here, as I say, we were having 10 to the minus 3 millibar of pressure in the trap. And on one of my last campaign in series, so the first apparatus that I presented you, where you can do ion mobility reaction. I mean, it's not the best precursor, but starting from naphthalene, we form some phenylium. And we look at it, the reactivity with water, and we could clearly see a big drop again here and going in the right direction in the reactivity toward water, going from basically singlet to the unreactive triplet state. And I just got granted some beam time to further pursue this using the series tandem mass spectrometer. So really looking forward to see what this will bring. And I just rapidly conclude. So I hope here I've convinced you how important it is to take into account this VUV photo processing of interstellar power. I think Christine Joblin has done already quite some work on that, on the unsubstituted one. But here, what I really want to stress is the importance of these isomerization processes, especially in the elucidation of these aromatic infrared bands and even understanding the difference of chemical network in different regions of space. And there's this really absolute need of absolute cross-section, which is really hard. As you have seen, I didn't present absolute cross-section for reaction, but not for photoionization or photodissociation, because this is quite challenging. And yeah, I mean, I don't know if it works or not, but it might be interesting to really have a close look of what could be important charge transfer reaction for astrochemistry if you have like two well-abundant species of decent size that could really interact and drive like chemistry in a direction that was not really necessarily expected. And with that, I would like to thank you for your attention.
All right, thank you, Ugo. We do have a couple of questions coming in the chat. So I'll take the first one initially. So someone is asking if you could perhaps comment a little bit more on the nature of those electronic transitions that you were showing, particularly with the pi electrons in the aromatic molecules going up to, I think, to the S12 state or orbital.
Well, I mean, yeah, I can. So I mean, what you can see here, I mean, this is again, it's a crude, it's TDDFT. It's based on TDDFT calculation, even like when we produce the spectrum for the benzonitrile here. So, I mean, you can see here, you conserve this. I mean, maybe here you see better. You conserve really this pi system. So it's just a pi star, typical, the classical transition, strong transition for aromatic species. Whereas in this case, you can clearly see that this is completely, you're breaking this pi system, and this is really speculative. I mean, it's just trying to make sense of this strange resonance effect in here that's exciting this S12 state. You will basically open a path where you can form C6H5 plus in like basically open the ring of C6H5 plus, and therefore you will completely prevent the reaction forming this cyclic, basically phenyl, protonated phenyl ions.
Yeah, and I think this actually kind of addresses the second question that came up in the chat, which was there a situation where the presence of the radiation alters the isomer of the PAH compounds? So in this case, I guess you have a situation very much like that. All right, another question has come in asking, can you talk about the temperature in your experiments?
Well, okay, so here it's basically it will be room temperature because you're just thermalizing. You have those helium buffer gas in the trap, so everything is basically so in those experiments is room temperature. The only thing which is not is this little bit of a spectrum that has been recorded in Marseille, which will cool down at a few tens of Kelvin, if I recall correctly. But I mean, yeah. So I mean, I see the point behind that. It's probably yeah, 300 Kelvin is not really the classical temperature in space. But I think the main problem of this experiment, if you want to relate it to astrochemical problem, if you really want to do a one-to-one comparison, I will give you a hint of direction to dig in to explain things in space, but it's rather the pressure. I mean, you have a lot of third body collision that will stabilize product that probably won't be the end product in space, as you will not have this collision to release it. And you can already see it in the case of the reaction of phenylium with water, with actually here, I didn't specify it, but what we are detecting here is not the protonated phenyl species, but it's the phenyl cation. So you have a H loss to stabilize the adduct.
All right. So I had another question as I was looking at this. For instance, like this figure that you've got here, you've got cross section on the y-axis, and I know that you had the caveat that absolute cross sections are very hard, but like, can you help me calibrate myself for like if one of these species has a cross section of 10 square angstroms, what does that mean about its lifetime? Like if that's like a photoionization or photodissociation cross section, what does that mean about its lifetime under like the standard interstellar radiation field?
So those are collision. So those are reactive cross sections. So that will not be that would be under the standard period of collision with with neutral partner or and that I have no idea. But that what we would have to look at it.
Yeah. Okay. Sorry, I was.
No worries on this.
Yeah. So one other question that I've seen, you've had theoretical calculations in here to help calculate things about the nature of electronically excited states. What, like, if you had, access to infinite computing resources, what kinds of calculations would you want to do to either help you guide future experiments or answer current unknown questions that you have in your research?
Well, that's a good question. So what I can tell you already is doing the similar kind of TDDFT, even using the octopus code from Giacomo and Giuliano, that worked fairly well for unsubstituted PAR and the work on of Christine Joblin using the same experimental setup. Doesn't seem to work so well when you add the cyano substituted one. So yeah, I mean, of course, I mean, as you increase the density of states, I mean, you probably will end up with a bunch of states that have some multi-configurational character and things. So, I mean, probably you will want to move towards some, I don't know, CAS-SCF, CAS-PT2 if you want to have the energy right. But I think it's not, I don't know. I think it's not really the direction you want to go with there. I mean, maybe the thing which is interesting is what I'm working on right now is to get the singlet triplet gap really precisely and trying to find a way. I mean, with only this experiment, just give you a hint, a flavor, right? Maybe with a series one with ion mobility, we'll get a better feeling of characterizing the singlet triplet cap. I mean, not so long ago there was a work from Jos Omens that shows spectroscopically evidence of triplet naphthelium, so basically and the C10H7 plus, actually using similar instrument.
Okay, I have another question for you. This one's a little bit perhaps more speculative. I've read in some cases that like if a PAH is embedded in an ice, that can alter its like ionization threshold. Have you thought at all, or do you study anything about like fundamental interactions that could alter the like either reactivity or ionization of PAHs in an ice context?
So there, I will speak take gloves because this is outside my expertise. But what I know here, we have people working on like looking at things on ices and stuff. And what it seems is what they looked at often is what happens if you irradiate ices with UV photon, or like if you deposit PAR or things like this with UV photon. And often what comes out is you just fragment little things. It's hard to dissolve large system, but the best way of like forming the thing in the gas phase is just to hit them with cosmic ray. So it's basically typically here in my lab is a work performed by Emmanuel Dartois. But in terms of the chemistry, I think also you were asking about how this can influence the chemistry. I mean, there are a few work that have been done, but the question is always a little bit hard because you need to probe what you're doing. And I think this is the main question, is like how much you influence things by probing what the chemistry that is happening on the ice surface. That would be my opinion from a non-expert in the field.
All right. Well, we are coming up to the end of the hour, so I think with that we're going to wrap things up for today. So thank you again, Ugo and Joan, for two very outstanding presentations. So you all know we are going to be off next month. So I hope those of you who are in a university environment, students or teachers like I am, good luck with the rest of your semester. We will see you back here in January. So you know, if we don't talk to you before then, you know, happy holidays, and keep an eye out for more information about our January AstroCheminar. Should be coming out somewhere around the turn of the new year. So thanks again for coming, everyone, and we'll see you next time.